So, what we are going to discuss is converging nozzle. It is a special case of variable area problem. Okay. So, I have a nozzle that is converging. This has some particular exit area. So, this is my exit. This is supplied from a tank where the pressure is P0, temperature is T0. So, this is my inlet. So, this outside pressure is Pb, back pressure Pb. I will assume isentropic flow. So, whatever we are going to derive is strictly within this assumption. So, from 1 to 2, 1 to 2, the flow is isentropic, which means in the TS diagram from 1 to 2, from 1 to 2 I have an isentropic flow. ds is 0 here, there is no Q, there is no Ws. So, there is no heat transfer and there is no Ws. So, associated with this there is a stagnation point. So, we have seen that this is equal to the stagnation state at the second point. The pressure is also equal. This is from your energy equation with the assumption that there is no Q and no shaft work. So, I have my stagnation enthalpy same. So, the temperature, stagnation temperature is also same. P02 by P01 is e power minus delta S by R, which is now 1. So, my stagnation pressure is also same. Since it is isentropic, we have also shown A1 star equals A2 star. So, your A1 star is also equal A2 star in this process, whatever we are doing here. So, in the entire section between any two sections in the entire stream here, we have A1 star equals A2 star. So, what we are trying to do is we will decrease our back pressure and see what happens to the flow. So, first let us keep P0 and T0 constant. Let us talk about P0 alone to avoid confusion. So, I am keeping P0 constant and my A2 by A1 also constant. I am not changing the area at the inlet or area at the exit. Now, Pb is continuously changed, Pb is changing. Okay. So, I do an experiment with different Pb. Remember, what we are going to do is a quasi 1D and steady problem, which means that the change is not happening in time, but we are changing the Pb and then watching what happens. So, I change my Pb to some value and see what happens at this point. I am not changing Pb continuously. Okay. So, there is no time variation. This is the steady process what we are going to do. All these examples that we are going to see is a steady process. So, these are all steady process. So, remember that. So, we will change this PB to a new value and see what happens, okay, without including the time variation. So, let us start with some value P0 10 bar and PB also 10 bar. So, this is a case where PB equals P0 equals PB and hence no flow. Okay. So, this is the back pressure I have. So, the inlet pressure is stagnation pressure is P0, which is giving you the gas. If the back pressure is also the same value, there is no pressure. So, your exit pressure P exit is also the same value, there is no change. So, your P0 equals P exit equals PB, no flow. Now, I decrease this PB further to 8 bar. So, as I told you, I am not continuously changing. This is a new experiment with 8 bar as my exit pressure. So, my PB by P0 is 8 by 10 equals 0.8. So, the Mach number associated with this ratio for gamma equals 1.4. Is around 0.75. So, the Mach number at the exit will be equal to around 0.75. No. Point 8 is around 0.57 from gas tables, okay, for gamma equals 1.4, okay. So, here my P exit is again equal to P0 because this is going to be a subsonic flow. So, the pressure here is also going to be the pressure at the exit. So, the subsonic flow, there is no change in pressure between exit and the ambient pressure. Now, I decrease my back pressure further to 5.28. So, that my PB by P0, P exit by P0 is 0.528. Okay. At this pressure, my Mach number at the exit is going to be 1 for gamma equals 1.4. So, if I have this pressure ratio, my Mach number at the exit is going to be 1. Now, if I decrease my PB further to say around 4, my PB by P0 is 0.4. The Mach number associated with this is 1.22, around 1.22. But the problem here is we had seen in the other class, previous lectures, to have a supersonic flow, the velocity, the area should be increasing, the dA should be positive, which is not happening here. Here the dA is always negative. Okay. Now dA is negative, inlet Mach number is subsonic, it has reached m equals 1 for some pressure ratio. Now if I decrease it further, you are getting a supersonic pressure ratio, this pressure ratio related to supersonic flow, but there is no area increase. So the flow cannot go beyond m equals 1. So it so happens that your m at the exit would still be 1 after you have reached this pressure ratio. So whatever you do, the back pressure, whatever back pressure you decrease to after this pressure ratio, your exit Mach number is still going to be 1, and it does not change, it does not depend on further on your Mach number. So what is happening inside the nozzle, after your PB by P0 reaching that particular pressure ratio is not going to affect anything inside the nozzle, if you keep your P0 constant and A2 by A1 constant. So what did we do? So we had the nozzle here. If P0 equals PB, there is no flow, which is also equal to your P exit. Now if I decrease my back pressure a bit, by a small amount, I would get a subsonic flow in the nozzle, which will exit out. So the exit would be equal to PB, P exit would be same as your PB, but it would be m less than 1, the Mach number at the exit is less than 1. But once I reach that ratio for m equals 1, my PB is equal to P, and if I call that as my critical pressure ratio, this exit pressure ratio is my P star. Such that my PB by P0 plus PE by P0 equals some P star by P0. This is equal to 0.528 for gamma equals 1.4. If I use different gas, I would get a different ratio, but for air you would get, if the pressure ratio is this, you are going to get m equals 1, and I call that pressure as my critical pressure, which is also our P star. Okay. So m equals 1 is also our star condition, which is at that area at this, for this particular ratio is our A star, which we will deal it a little later. But for the time being, m equals 1, PB equals PE equals P star. Now if I decrease my PB further, nothing would happen here. My PB would be much less than my P exit, but P exit would still be equal to P star. So this value is not going to change. So this is m still equals, m at the exit is still 1, the Mach number at the exit is still 1, but the flow does something here, which again we will deal it after studying shocks and other things, what happens outside the nozzle. At present we are dealing only with what is happening inside the nozzle. There is nothing that is going to happen after PB reaching your P star. Okay. So once that is done, the point here is the Mach number at the exit is not going to increase other than 1, even if you decrease your PB. So if your exit pressure is this or below, your Mach number at exit is always going to be 1 for a converging nozzle if you keep your PB constant. Okay. So, you keep decreasing your PB, no matter how much you decrease, if this is there, this is what you get. Okay. So, if I have a nozzle, P0, PB, P exit. Now, I have a nozzle, PB by P0 is say 0.4, PB by P0 equals 0.4, which means that the Mach number here is 1, okay, and I have something that is happening outside the nozzle. Now, what I do is I cut this nozzle to this value, keeping the same back pressure. Now, if I do this, if you look at whatever we have done here, the area ratio does not come in the physics. So, whatever I do here, keeping PB, P0 constant, that is very important. If we keep, you have to keep P0 constant and then do this process of cutting this nozzle into 2. Since the area ratio is this, we are still going to get m equals 1 here. Or if I elongate this, again since PB by P0 is this, I am still going to get m equals 1. So, this condition is not going to change. This is the so called chalked condition. So, whatever you do, the m exit is always 1. And your area at the exit becomes your A star. What does that mean? So, I have some Mach number here. I am doing an isentropic process to bring my Mach number to 1. I am doing something to do take it to 1, and that value of the area is your A star, which is precisely what we are doing. It is an isentropic process, we are bringing it to 1. Okay. Now, when I said for given Mach number, I am reducing it to 1, and this would be your A star. But here I am cutting the A star, still I am getting M1. So, the process here is, so for example, what I have told you here is, for a given Mach number here, how did we define our star condition? We have the TS diagram. So, the process is from 1 to 2. So, I have state 1, I do something to take it to, I do an isentropic process to take it to velocity 0, which is my stagnation. I take it to a state where velocity is same as my sound velocity, which is my star condition, which is my m equals 1 condition. Now, that is precisely what I am doing here. I am taking this state to a state where my Mach number is 1. So, this is my star condition, but I have also told you, even if I cut this, I am still going to get m equals 1. So, this does not mean that I have 2 A star here, but rather when I do this process, something is happening to the inlet Mach number, but I am keeping my P0 constant. So, something is happening, which that something is not what we are going to study, that is a non-isentropic process which we will not deal with. Okay. So, whatever that is happening here is 1, and that is associated with the chalked condition. Okay. So, for this P0, if the pressure ratio is below 0.5 to 8, that is a chalked condition. Okay. So, this pressure ratio here is my chalking condition for the converging nozzle. If it is below than that, it is always going to. So, in the chalked condition, what would be the mass flow rate? So let's evaluate the mass flow rate at the exit. M dot is, or M dot by A is rho into V, P by RT into V. Now I take RT here, then V multiplying root gamma by root R. So there is a root gamma here. Then I multiply and divide by T0. Okay. So what I have done here is I have taken one root T here. There is one root T missing. Okay, there is 1 by root T. So what I have done here is I have taken one root T here, another root T here, multiplied and divided by root gamma, multiply and divide by root T0. Okay. So PV by root gamma RT, that would be my M. I write gamma here by R, and then root T0 by T, and I take that root T0 here. So this would be my P by root T0 into M, because this is my velocity of sound, into gamma by R. T0 by T is 1 plus gamma minus 1 by 2 M square. Now there is a root here, so it will be 1 by 2. So my M dot by A into root T0 by P is nothing but M into root gamma by R into 1 plus gamma minus 1 by 2 into M square to the power 1 by 2. So this quantity is going to depend only on your Mach number at the exit and these things. So your Mach number at the exit is going to depend on these ratios. I can change P also in terms of Mach number by multiplying and dividing it by P0, and I write this quantity. So this is equal to P by root T0 into P by P naught is 1 plus gamma minus 1 by 2 M square to the power into, there is an M here, there is a root of gamma by R into 1 plus gamma minus 1 by 2 M square to the power 1 by 2. So this I will reduce this to T0 M root of gamma by R 1 plus gamma minus 1 by 2 M square to the power minus gamma plus 1 by 2 gamma minus 1. Okay. And there is a bracket here. So my M dot by A in the root T0 by P0 equals function of M, gamma and R. So my mass flux is now depend only on my stagnation temperature and pressure. So if there is a change that is needed, you have to change your stagnation pressure or stagnation temperature. So when I have a nozzle, my PB will decide, the pressure ratio PB will decide my mass flow rate till m less than 1, that is when my P exit is P star equals PB, my mass flux is decided by PB by P0. But once it has reached this stage, any further decrease, in PB will not affect the exit Mach number, okay, and hence will not affect my mass flux. Okay. So if I want to change my mass flux, I need to change my P0 and T0. Okay. So that's your chalked condition. So that's what typically happens when you have a converging nozzle with decreasing PB. And remember, this is an isentropic solution that we are doing, and the stagnation temperature and pressure is kept constant during this exercise. Okay. So if I plot m dot or m dot by A into root T0 by P0. So this is my B by P0. So when PB by P0 is 1, no flow. When PB is reduced, you will get a mass flow rate according to this equation which we have just now derived. So you would get a mass flow rate according to this equation, which would be like this. So this would be according to this equation, which is m into m dot by A root T0 by P0 is a function of Mach number R and T0. Mach number at the exit, because you do not know what is the Mach number at the exit. So this is Mach number less than 1, your P exit is not yet equal to your P star. So your P exit is same as your PB, which is greater than your P star. But once your PB reaches P star, so your PB by P0 equals P exit by P0 equals P star by P0, you would get m equals 1. And once m equals 1, once you reach m equals 1, if I substitute m equals 1 in this equation, what I would get is m dot by A root T0 by P as m into root gamma by R, 1 plus gamma minus 1 by 2 m square in minus gamma plus 1 gamma minus 1 into 2. So, when m equals 1, I substitute this would be root of gamma by r 1 plus gamma minus 1 by 2 to the power minus 1 plus 1 2 gamma minus 1. So, this is gamma plus 1, this would be root of gamma by r into 1 plus gamma by 2 to the power minus gamma plus 1 by 2 gamma minus 1 brackets. Okay. So, once you have reached m equals 1, this is your value, and after that whatever you do with your PB, keeping your P0 constant, your Mach number is not going to increase at the exit. Hence, your mass flow rate is also going to be a constant after this. So, I am doing this process, I am decreasing my PB. So, after that my m dot is constant, and this value is this root gamma by r into 1 plus gamma by 2 to the power whatever that is written here. I will write it neatly here. This value would be r by gamma by r 1 plus gamma by 2 to the power minus gamma plus 1 divided by 2 gamma minus 1. So, that would be the value here. So, this is a case when we keep P0 constant. Okay. So, P0 is kept constant, we are changing the PB, so that this ratio is reducing, and it is reducing initially, and that decides what is the mass flow rate till it reaches Mach number 1. Further than that, the Mach number at the exit is not reduced, hence the mass flow rate is not reduced if you have this condition. So, this is the maximum flow rate, maximum mass flow rate, it can go through that particular area, because the area is here. So, your mass flux, this is 0. So, at m equals 1, m exit equals 1, your A exit is your A star, and your mass flow rate or mass flux is maximum at m equals 1, which is now just root of gamma by r into 1 plus gamma by 2 to the power minus gamma plus 1 by 2 gamma minus 1. Okay. So, this is m dot by A into root of T0 by P0, which would be maximum at this rate. So, this is a constant value. So, mass flow rate, mass flux is maximum, this ratio, and this is a constant value. So, it depends only on your fluid. Okay. So, again I will conclude with explaining this particular plot again using the setup we have just now shown. So, what I am going to do is I decrease my PB, keeping my P0 constant. So, I keep decreasing my PB, which means PB by P0 is slowly decreasing from 1. When this is 1, there is no flow, I keep decreasing. So, there will be a flow that is starting, that is all subsonic till it reaches the pressure ratio of 0.0528 for air. Once it reaches that, the exit Mach number is 1, and once the exit Mach number is 1, whatever further you decrease, the exit Mach number is not going to change, and hence if you look at the equations for the mass flow rate also is independent of the pressure ratio what is there. So, the pressure ratio is not going to play a role in the mass flow rate, and that is the chalked condition, because you are chalking your flow with that particular pressure ratio. Okay, so the message from today's classes, we have kept P0 constant, PB kept on decreasing. So when we reach PB by P0 equals P exit by P0 equals P star by P0. When you get this value, you reach m equals 1 at the exit, which is also your chalked condition. Further decrease in PB has no effect on your exit Mach number and no effect on your mass flux. So if you want to increase your mass flux or decrease your mass flux, you have to change these values, A or P0 or P0. Okay. So when m equals 1, you can also call this as your A star. So this can also be typically called as A star, okay, because m equals 1. So with that, I would end today's lecture, and we will take up in the next class a continuation of this.